Hello everyone, my name is Edward Liu and I am a second-year PhD student in the Electrical and Computer Engineering Department at Carnegie Mellon University. Today, I'm going to be presenting our work on a cross-platform dynamic split rendering system which we call RenderFusion. RenderFusion aims to enhance real-time rendering for mobile XR devices. The best real-time rendering system for XR aims to optimize three things: mobility, visual quality, and responsiveness. Each of these elements must be balanced in a way that gives the best quality of experience to users. Currently, a lot of XR devices have rendering computations done entirely locally on the device. This lets us get really low latency interactions like the video on the left. However, local rendering limits us to having only low-resolution objects in our scenes. Let's see what happens when we try to render a very high-resolution 3D object on the Magic Leap 2. What you see here is the real behavior of a web browser on the Magic Leap 2, attempting to render a high poly count object. If we decimate the model to a reasonable poly count, we're able to render it again at high frame rates, but the model is nowhere near as high quality as the original. Clearly, local rendering isn't enough to render everything we want at high qualities, especially on mobile headsets. Instead, we can offload all rendering computations to a remote server with powerful processors and GPUs, and stream results back to the headset. This is going to produce much higher quality images, but at the heavy cost of latency. Now, inputs need to go all the way to the remote server and all the way back to the headset to be viewed. Here, I show a remote rendering server sending results to a client through the network. The client sees a delayed frame from the server and needs to perform reprojection. And, to make matters even worse, not only is latency bad, but we have to deal with unreliable and unpredictable networks. We see that local rendering has low quality, but can be very responsive. We also see that remote rendering has high quality, but high latency. So, why not combine the best of both worlds? Split rendering is a way to render some things locally and other things remotely, combining the best qualities of both local and remote rendering. In a split rendering system, you typically need some kind of heuristic to determine which objects get rendered where. In state-of-the-art split rendering systems, both in commercial and academic systems, there are usually two main schemes. The first is a static determination, typically at the beginning of an application, based on some criteria that an object needs to satisfy. This is done in Azur's hybrid rendering for the HoloLens, where UI elements are rendered locally and everything else is rendered remote. The second schema is a distance-based dynamic determination. The idea is basically that objects that are closer to the camera are more likely to be interactable, so they need to be pushed local, and farther away background objects are pushed remote to keep the resolution high. This technique can be found in many academic works. While this may seem promising, what if you have a close-up object that needs to be high resolution? For instance, as this user approaches a high-resolution virtual car, the frame rate of the device immediately drops. This means a distance-based schema cannot handle high-quality foreground objects or changes in local device workloads. While we could decimate all foreground objects, this needlessly sacrifices quality. Specifically for us, we've been working on an open-source spatial web implementation called Arena. Arena maintains a database of various 3D scenes containing any number of objects of any complexity. Devices query Arena to find out which objects they need to render for the scene. Browsers on higher-end devices can easily render any object you throw at it. However, a scene can contain many high-resolution objects that can overload some browsers on some lower-end devices. An extremely lightweight client might not even be able to render the scene at all. Instead, we can use remote rendering to ease some of the rendering computation on some devices. With this, we have a true networked scene that can be rendered by any client. We can use split rendering to add graceful degradation to Arena, but we need a more intelligent scheme to determine which objects get rendered where to mitigate the problems I mentioned earlier, which are made worse when running rendering on web browsers. And thus, we created RenderFusion. Now, I'll briefly talk about our implementation. Our local machine runs an Arena web client, and we use Unity for our remote rendering engine. Walking through the RenderFusion workflow, the browser begins by sending system metrics to our decision-making model, which uses this information to update the Arena networked scene on what the current rendering assignments of each object should be. Arena's Scene Manager updates the local and remote machines on each object's state if changed. While this is happening, the local client then sends the remote rendering server the current camera pose, controller inputs, whatever the remote rendering engine needs to perform remote rendering. The server then renders a frame at that current pose and streams the result back to the client. Since we are bound by Arena's web implementation, we use WebRTC for streaming. Note that while WebRTC is a popular streaming technology, it's not super ideal for low latency applications like remote rendering. we send both color and depth frames of the left and right eye stitched side by side. Then, the client performs reprojection to account for temporal discrepancies. At the same time, the client does local rendering at its own pace. Lastly, the local client will merge the remote and local frames to produce a coherent result before sending it to the display. We perform reprojection to account for temporal discrepancies. To simplify implementation, reprojection is performed using asynchronous time warping. However, the transformation produces disocclusion artifacts shown in black in the second image. We can hide these artifacts by inpainting the nearest pixel. While it may look very noticeable on 2D screens, the smearing caused by the color infill may actually be partially blocked by the eyepiece of a headset and will most likely be in the user's periphery unless latency becomes very high. In RenderFusion, we try to render objects that touch the viewport edges locally to reduce artifacts. In RenderFusion, an object can have 3 representations. Each representation has its pros and cons, and we attempt to take the pros of each. We can render an object locally at its highest resolution, giving us the best quality and response latency, but using the most local resources. We can instead decimate an object and render it at a reduced resolution, giving us low resource usage with low latency, but at the cost of visual quality. We can also render an object remotely at its highest resolution, giving us minimum local resource usage along with high qualities, but that object now has the highest response latency. The most important step in RenderFusion is to determine which representation is best at a given time. This decision-making problem is formalized as follows. For all objects in the scene, we want to find the best rendering medium for each object to maximize over total importance or benefit towards a good quality of experience. Benefit is modeled in our paper using metrics like object interactivity, latency masking artifacts, object visual quality, and network bitrate, among others. We maximize over benefit with the constraint that the total poly count of all locally rendered objects is less than some estimated threshold. Then, we run an optimization solver to find the best rendering mediums for each object. For our decision model, we needed to know at what latency users start to notice controller delays and latency masking artifacts. For this, we created a web-based remote rendering simulator to perform user studies in VR. With this simulator, we can induce artificial delays to controller inputs and rendered frames. We apply the same reprojection technique we use in the real system to the delayed frames in the simulator, producing the same reprojection artifacts. Using our decision model and estimated latency thresholds, we employ dynamic object swapping at runtime to adapt to heavy client workloads. As the user approaches the statue, it swaps to remote to show it in high quality and relieve the device of rendering. We also adapt to changes in network quality. Since the network in this video is very poor, RenderFusion will swap objects to be locally rendered to preserve quality. To evaluate our system, we conduct another perceptual study, comparing RenderFusion to pure local rendering and pure remote rendering on the web. We also compare RenderFusion's performance under typical and delayed networks. In our paper, we show that users preferred RenderFusion's mixed quality overall. For this scene, since RenderFusion renders some foreground objects remotely at high resolution, it appears to have a higher quality than local rendering. RenderFusion's background model is rendered locally at a reduced resolution to avoid reprojection artifacts. This means, when compared to remote rendering, RenderFusion produced less artifacts and, again, appeared to have higher quality. We also show that RenderFusion has the same latency as local rendering. And massively improves the latency when compared to remote rendering. Overall, users preferred RenderFusion's mixed quality with its low latency inputs. In summary, we present RenderFusion, a split rendering system for WebXR clients that uses a decision model to partition a 3D scene into local and remote rendered objects. We show models for per-object benefits towards quality of experience and model the effects of controller delays and reprojection artifacts. We also provide open-sourced implementations, which can be found in the links here. For more information and for specifics, please check out our paper. Finally, the beauty of Arena and the web lets us run RenderFusion on any device like laptops, mobile phones, headsets, and many other devices. Thanks for listening.